Just like with substitution, we can do integration by parts multiple times if we need to get, a result. So for example, here, we're going to have the integral of x squared e to the x dx. So I'm going to look at this and I'm going to say, okay, u is going to be my x squared. And this is going to be my dv. Because I know, again, I'm looking for something that when I take the derivative, it gets simpler. So if u equals x squared, that means that du dx is going to equal 2x. And that means that my du equals, let me rewrite that cleaner here. To x, and my du is equal to 2x dx. Sorry, this should be a v dv. So my v, no, it's just my dv, sorry. My dv is equal to e to the x dx. And that means that when I integrate it, I'll have v equals to e to the x. And again, technically you should put a c on there, but because we know it's going to show up later, we shorthand and skip over it. So we know the expression, the integral of u dv is equal to uv minus the integral of v du, which in this case is u is x squared, and then v is e to the x minus the integral of v, which is e to the x, du, which is 2x dx. And now, unlike before, this, we don't know how to integrate this, right off the bat. But I can use integration by parts again. And that's because I look at this 2x and I say, well, it is simpler than before. It was x squared, now it's 2x. So let me try that again. But first I'm actually going to rewrite this for reasons that I know from practice. It's nice to pull out as much as possible in a constant. So I'm going to pull that 2x, that 2 out, and leave my e to the x, x dx. And now we've got a new integration by parts where I'm going to say my u is equal to x. That means that my du is going to equal to dx. You can run the whole math to double check that. But I'm going to save some time by skipping over it. My dv is going to equal e to the x dx. The nice thing here is we already did all that math above. So I know that v is equal to e to the x. And then we have a new u dv equals uv minus the integral of v du. And this, recall right here, is just for this expression here. We will have to add back in the x squared e to the x at the end, but I'm just working on this second derivative bit, or the second term bit. So that will be u is x, v is e to the x minus the integral of v, which is e to the x, du, which is dx. And this, when we integrate it, we'll get x e to the x minus e to the x plus c. And so see, there is where our constant integration comes in. I don't need to worry about it coming from earlier. So all of this is the integral up there. So that means our final answer is x squared e to the x from the first term minus 2 because again, I said pulling this out will make my math life just a little bit easier, times everything that I had right here. Now, let me write it down so I don't lose you, but we're going to show how this cleans up plus c. So now if I distribute this, which you don't have to, but I will, technically this would be plus 2c, right, if I distribute proper, like standard. But because c is an arbitrary constant, it's just saying that it could be literally any constant you want. There's no reason to write a 2 in front of it, because if I wanted to pick my c as 5, and then it gets multiplied by 2, I could just as easily have written c and picked 10 instead. So because it's an arbitrary constant, multiplying, dividing, adding, subtracting from c is just going to change that arbitrary constant slightly. But again, it's supposed to represent all values and no values, one of any of the values. So that's why we typically, when we multiply, divide, add, or subtract to those constants of integration, typically we just absorb whatever changes and just rewrite it as c. So this is our final result. If you want to test it, you can go through and take the derivative, and you'll see that you end up getting what you had originally, assuming I didn't make a mistake in here. The point here was after we started, we ended up with an integral that was simpler, but not simple enough to take the integration of immediately. So we had to use u substitution a second time to finally get to an integral that we could integrate kind of just on its own.